All right, let's talk about a machine that you've probably seen 100 times, even if you didn't know what it was. You know, those giant towers at oil refineries and chemical plants? Well, we're going to dive into how they work by asking a question that honestly sounds like it breaks the very first rule of engineering. So here's the paradox. I mean, think about it. Every engine we build, from a car to a power plant, is all about one thing: efficiency, right? We're always trying to squeeze every single drop of useful work out of the energy we put in. But what if the entire point of a machine was to be the exact opposite? To be, profoundly and purposefully inefficient? Well, that machine exists, and it is the distillation column. Seriously, this thing is the absolute workhorse of the entire chemical industry. And its big secret, the thing that makes it work, is that it's designed to just chew through the quality of energy, its ability to do useful work for one single purpose: to create something incredibly valuable: purity. Okay, to really wrap our heads around this, we need to completely reframe what a distillation column is actually making. Because it's not just about pure chemicals. The real product is, well, it's a concept from thermodynamics. Just think about this for a second. If you pour some cream into your coffee, what happens? It mixes, right? All by itself. It doesn't need any help. Things in the universe just, well, they naturally move from a state of order to a state of disorder. It's one of the most fundamental laws of physics. And it's all driven by this thing called entropy. And that right there is the key. The reverse process, unmixing, is totally unnatural. It just doesn't happen on its own. You have to force it. I mean, could you imagine trying to get that cream back out of your coffee? It would take a ridiculous amount of effort and energy. And that's the point. Separation always costs you something. It always has an energy price tag. So that energy cost, that absolute bare minimum amount of work you'd need to do to unmix something, that is what distillation is really creating. We give it this cool name, negative energy, but really it's just the value of the order we've created. That's the product we're selling, not just the chemical, but the order itself. So if we're going to pay for this order, how do we keep the book straight? How do we account for the cost? Well, just talking about heat isn't going to cut it. We need a much sharper tool, and it's called Exergy. And here it is, Exergy. The key thing to get about Exergy is that it's not about how much energy you have, it's about how good that energy is. Its quality, its actual potential to do something useful. So super hot steam, that has a ton of Exergy. Lukewarm water, almost none. You can think of Exergy as the universe's real currency. It's what you actually spend to get work done. Okay, so this table breaks down the key players in this whole drama. You've got Gibbs free energy, which basically tells you the theoretical best you could ever do. It sets the goal. Then there's enthalpy. That's just the raw heat energy we're pumping in. Entropy, of course, is the villain. It's the disorder we're trying to fight. But the hero, or maybe the strict accountant of the story, is Exergy. It keeps track of everything. And the amount of Exergy we destroy, well, that's the real cost of the process. That's the true measure of our inefficiency. And this brings us right to the heart of the matter. This inefficiency, this destruction of Exergy, it's not some flaw we're trying to engineer out of the system. It is the system. It's the engine. It's the price you have to pay to make separation happen at any kind of reasonable speed. See, a perfectly efficient process would literally take forever. So to get anything done in the real world, you have to be inefficient. And there's actually a physical law that proves this, called the Gouy-Stodola theorem. It sounds complicated, but the idea is simple. It says that the lost work, the Exergy you destroy, is directly tied to the amount of disorder, or entropy, you create. So look, to make separation happen, you need driving forces. To get driving forces, you must create entropy. And to create entropy, you must destroy Exergy. There's no way around it. So the big question is, how does the column pull this off? How does it manage to create all this order on the inside without, breaking the fundamental laws of the universe? Well, it turns out it has a really clever trick up its sleeve. The strategy is actually brilliant. The column can get away with making things neat and tidy, creating a low-entropy state inside itself, because it's not a closed box, it's an open system. And what it does is act like a giant entropy pump. It sucks the disorder out of the chemical mixture and just dumps a whole lot more of it out into the environment. So here's how this pump actually works. Step 1, you pump in a bunch of high-quality, high-temperature heat at the bottom of the column. This energy is low-entropy energy. Step 2, that heat turns liquid into vapor, which travels up the column, doing the work of separation along the way. And then, step 3, at the very top, You pull that heat back out using a condenser, but, and this is the crucial part, at a much lower temperature. And because of some cool physics, low temperature heat carries a massive amount of entropy with it. So you're basically exporting all that disorder out of the system. This whole setup is basically a giant, real-world version of a famous thought experiment called Maxwell's demon. The idea was this tiny demon that could sort fast and slow molecules. Well, every single tray inside that column is doing exactly that. It's sorting molecules. The more volatile ones get to go up, the less volatile ones have to go down. And the payment for this molecular sorting service, all that exergy we're destroying, powered by that constant flow of energy from the hot bottom to the cool top. Okay, that's the theory, but let's get practical. How does an engineer standing in a control room actually manage this? How do they decide exactly how high a price to pay for purity? All right, let's look at where the money or the exergy is actually being spent. The biggest line item by far is the reboiler and the condenser. We're talking half of the entire exergy budget gets destroyed right there. That's the price for moving heat around. After that, a pretty big chunk, about a quarter, is spent on the trays themselves, actually forcing the molecules to separate. The rest is smaller stuff like friction. Now, you might think a system this complex would have a million dials and buttons, but really, engineers have one main control knob for the whole show, and it's called the reflux ratio. All it is a measure of how much of the good, pure stuff you collect at the top you decide to send back down into the column to help with the separation. And cranking up that reflux ratio, well, it's pretty much like flooring the gas pedal. The more liquid you sent back down, the more you have to reboil at the bottom. And that means your energy bill just skyrockets. You are literally making the choice to destroy exergy at a much faster rate. So why on earth would you do that? Why just burn money? Well, because there's a trade-off. Pumping all that extra energy through the column creates way stronger driving forces for the separation. And that means you can get the job done with a much smaller, shorter column. So you're trading a higher energy bill, your operating cost, for a cheaper piece of equipment, your capital cost. It's a classic engineering trade-off. So, you see, it all comes down to this. When an operator in a plant adjusts that reflux ratio, they're not just wasting energy. That's the wrong way to think about it. What they're really doing is making a very precise economic decision. They are choosing to invest a specific rate of exergy destruction to hit their target for purity and production. So let's just recap this whole new perspective. The real product of distillation isn't a chemical. It's negative energy. It's order. The cost isn't just steam, it's destroyed exergy, the work potential you burn to create that order. And the inefficiency? Well, that's not a bug, it's the feature. It's the engine that makes the whole thing run. This machine is built to purposefully consume work potential to create order out of chaos. And that kind of leaves us with a bigger, more profound question, doesn't it? If creating something as simple as a pure chemical costs so much, if it requires us to purposefully destroy the universe's potential for work, then what's the hidden thermodynamic price for all the other much more complex order we see in our lives? In our technology, our cities, our societies, maybe even within ourselves. How much inefficiency does it cost to keep it all from falling apart?